welcome everyone. I'm Rick Moog, a faculty member in the chemistry department here. I want to thank the Common Hour Committee for improving our visit here today with Mark McDaniel, and I want to thank the Faculty Center and the Provost's Office for sponsoring today's Common Hour presentation. I know we're going to have a really stimulating and interesting talk coming up, so I'm going to try to keep my introduction as brief as I can. I'm very pleased to be introducing my friend and colleague, Professor Mark McDaniel, who is a professor of psychology at Washington University in St. Louis and is the co-director of CIRCLE, which stands for the Center for Integrative Research on Cognition, Learning, and Education. Washington University in St. Louis is actually a slight misnomer because Washington University is actually in Clayton, Missouri, which by coincidence is my hometown, which is the main reason I wanted to invite Mark here. Anyway, Professor McDaniel received his bachelor's degree from Oberlin College and master's and PhDs from the University of Colorado in Boulder. He's had a long and distinguished academic career in the field of psychology. Professor McDaniel conducts research in the general area of human learning and memory. Much of his work has focused on the application of cognitive psychological principles to education, and that's what he's going to be talking to us about today. He's also worked in the general area of human learning and memory, including projects on investigating the learning processes by which people acquire complex concepts. He's published over 200 articles, chapters, and books in the area of human learning and memory. And recently, about a year ago, there was a book released that he was co-authored with a colleague in the psychology department at WashU and actually a novelist, which is entitled Make It Stick, The Science of Successful Learning. And that book's going to be available here today on the tables in the back. And when the Common Hour is over, Professor McDaniel will be back there for a few minutes to talk with people about the book if they're interested, which I'm sure you will be. I want to just give you two brief quotes from reviews of this book to give you a sense of why I think it's great that he's here to talk with us today. And the first of these quotes is one that I want to particularly direct to students. This is a quote from one of the reviews of his book. "Learning is essential and lifelong. Yet, as these authors argue convincingly, people often use exactly the wrong strategies and don't appreciate the ones that work. We've learned a lot in the last decade about applying cognitive science to real-world learning, and this book combines everyday examples with clear explanations of the research. It's easy to read and should be easy to learn from, too." The second quote from a review of this book I want to direct particularly to my colleagues on the faculty, and this is a direct quote from this reviewer. "If I could, I would assign all professors charged with teaching undergraduates one book, Make It Stick, The Science of Successful Learning." So I think we're in for a very interesting and thought-provoking presentation this morning, so please join me in welcoming today's Common Hour speaker, Professor Mark McDaniel.
Thank you, Rick. It's a real pleasure to be at Franklin and Marshall. As Rick mentioned, I went to Oberlin College, which is a similar kind of liberal arts college as Franklin and Marshall. And what I love about these liberal arts colleges is that I think the faculty and students alike share an enthusiasm for learning. And so I'm hopeful that you'll be enthusiastic about my presentation today because it's going to focus on learning. What I want to do today is I want to appeal to the science of learning to identify some principles and techniques that we could import into the classroom to improve student learning and improve instructional effectiveness. Now, when I talk about these things to instructors at WashU or to students at WashU and other places, a common reaction is that they say, well, I find the laboratory work interesting and it's provocative, but before I make changes in my classroom, I'd like to see more classroom experiments. I'd like to see that these techniques work in the classroom. And students say the same thing. They say, before I'm going to change my study habits, I want to see evidence that they work with authentic materials. So, in the past several years, we've been working hard at our center, and others in the field have been working hard to try to transport experiments on learning into the classroom. And what I want to do today, one of my main themes is going to be to share with you, whenever possible, classroom experiments that emphasize the potency of the techniques I'm going to talk to you about. So what I'm telling you is this. I'm not going to just say, based on the laboratory we think this works. I'm going to say, here's the classroom evidence from experiments published in the last 3 or 4 years that it works. Now, another theme that I want to emphasize is related to the following comment. Whoops, I already have it up here. That comment is, why are active learning methods so seldom used in colleges and universities? This comment comes from an article in Scientific American last summer on the science of learning. And it's a comment that Carl Wyman made. It's a question that he posed. Carl Wyman is a Nobel Prize-winning physicist and more recently an award-winning physics educator. And he has promoted the idea that we ought to try to, as much as possible, eliminate lecture in the classroom. And that we ought to replace that with student groups that are working on problems with discussion questions that get to deeper understanding, with clicker responses that allow students to engage in classroom. And he's got some evidence that suggests that that does promote more learning in physics than, say, a typical lecture classroom. So he asks the question, why are these active learning methods so seldom used? And he presents several reasons which I think are good. But I think he misses a really important answer to this question. And it's the following. In Carl's work, he receives grants of millions of dollars to hire armies of postdocs to help prepare for 2 or 3 years the particular problems, the particular discussion points, the particular clicker questions that students were going to struggle with in class. This was a 2 to 3 year development effort to develop 1 semester, even less than a semester, of an active classroom. So I will ask all the faculty in the room here, how many of you have 2 or 3 postdocs to help you revise your course into this kind of course? Don't be embarrassed, just raise your hands. Let's see all the... There's not a single hand raised. Not a single hand raised. Nobody has 2 or 3 postdocs to help them revise their classroom into these reverse classroom situations with penetrating discussion questions and so on. It's a daunting task for a faculty member to do that. That's a big answer to this question. One of my themes is going to be, we don't need extensive revisions in the classroom to promote gains in student learning. What I'm going to suggest is that the methods and techniques that I'm going to identify can be adopted in the classroom with very minor variations in the classroom. Every faculty member could incorporate these in the classroom with good gains to student learning. And similarly, students don't have to change their study practices extensively to get gains out of the work they're doing when they're studying. So that's a theme in today's talk, and I want you to think about that as we present data. So I'm going to present part of the talk, a lot of the talk is going to be evidence to support the claims I'm making. And I want you to recognize that these kinds of techniques do not require extensive revision. All of us can use them. Okay. So what are students doing now? Well, here's some answers that I enjoy from the Kaplan Test Prep and Admission Survey. That, as you know, Kaplan is a corporation that helps students prepare for high-stakes entrance exams in med school and so on. And they ask the students, what do you do when you prepare for these tests? Here are some responses. One student said, I eat Alaskan salmon for breakfast. Well, I mean, the ideas are trying to get omega-3s in the brain. It helps brain health, and maybe it does, maybe it doesn't. but I'm sorry, it's a little late in the day to be eating salmon to try to improve your MCAT score. Another student said, I watch back-to-back episodes of ER. Well, you know, ER has some reasonable information in it, but it's also chock full of information that's not correct. And we know from studies in cognitive psychology that this misinformation is very easily incorporated into our knowledge and misleads students. So this is really a bad idea. This is not a good idea. My very favorite is the following. One student said, I wear my Superman underwear. Well, I don't know anybody who would do that. That's the silliest thing in the world. Who would wear, oh, how did that slide get there? Well, yes, it's fun to wear, not probably especially useful for learning. What are students being told? Well, this is a snippet from the St. Louis Post-Dispatch, the newspaper, that had subscribed to a series of newspapers in education, and they would run a small article every couple weeks for parents and for educators and for students on how to improve learning. And this is one that was oriented toward how students should prepare for tests. And it says what the student should do is repeat, repeat, repeat. If you have to remember a list of words, for example, read it over. Read it once and do this over and over again until you know it. Repeating what you have to remember can help burn the information into your memory. I will spare you the details of the 50 years of research that show that this is just flat out wrong. This is incorrect. Our intuitions is that we ought to repeat, repeat, repeat for better retention and learning. That's just not true. What are students? So this is, I think, a real problem, is that in the mass media, educators and students and parents are being told really poor information about how to improve learning. What are students doing? How are students studying? Well, we surveyed 1,294 middle school students in the St. Louis area and not as many high school students, about 102, and we asked them, how do you study? Well, 41% of the middle school students and 55% of the high school students said they repeated facts and key terms over and over again. In other words, at least half the students in middle school and high school are going about studying in a way that's not effective at all. They're not using their time well. What about college students? What about students at Franklin and Marshall? I don't know about students at Franklin and Marshall, but I do know about students at Washington University. A survey that was published 5 years ago asked Washington University students, how do you study for your exams in your class? And 84% said they reread the notes, their notes or the textbook. They reread. 55% said rereading is my #1 study activity. Now, we know from work in the laboratory with rather impoverished materials, word lists, paired associate lists, that repeating over and over again is not a good way to learn. And the question I've posed is, well, what about when you're reading more complicated material? On the one hand, you might think that's not very effective based on the laboratory work. On the other hand, things get more complex when we're dealing with connected discourse and connected units of knowledge. In that case, there's a theory from cognitive science that rereading might help because it allows the student to develop a deeper understanding of the material. So the idea is, on a first reading, you might get a sense of the individual facts, and on the second reading, about how a neuron works, for example, and on a second reading, you would build what we would call a better mental model of how that neuron works, or a better mental model in microeconomics of how fiscal policy influences the economy, or a better mental model in biology about how cell division works. So the idea is that maybe rereading is in fact effective because it helps students create a better, more coherent understanding. So really, now we've got two opposing theories. On the one view, it says, yes, reread to build better understanding. And the other view said, no, just repetition over and over again doesn't help at all. So we conducted an experiment. It wasn't in the classroom, but it was with authentic educational material to try to get an answer to this issue of, is rereading effective for students as a study activity, or is it in fact really ineffective? So we did a really simple experiment. This is not a tough experiment. We had students read introductory psychology textbook chapters either once, one group of students did that, or they reread their textbook chapter, as students say they're doing to study. We then developed what we thought was a fairly authentic exam, if you will, a test. We gave them a test consisting of 22 multiple choice questions and 4 short answer questions, and the short answer questions required explanation. For example, it required the student to explain how an axon can send an action potential down that membrane. So that would be one of the questions after reading a biopsych chapter. And here are the results. So first of all, let me show you the multiple choice performances after reading once or twice. Does reading twice help? No, it doesn't help at all. Reading twice doesn't produce any additional learning over having read the chapter once. Well, maybe you'll see it benefits on the short answer question, because that's where we're interrogating, if you will, students' understanding of how things work. That's where we'll see a benefit. No benefit. No significant difference between reading the text once and reading the text twice in terms of learning gains. But you might say, well, that's just an immediate test. So we took half of the students and we brought them back a day later to the lab. We gave them a delayed test to see what happens over relatively long term. And here's what happens. What happens is no difference between reading once and reading twice on multiple choice. No difference on short answer and reading twice. But we were a little bit, we weren't worried, but we thought, well, abnormal psych, students love that. And so maybe when they're reading once, they're really engaged and they're learning everything they possibly can. What about a different kind of chapter? What about a biopsychology chapter in which students have to learn about neurons and hyper polarization of the membranes and stuff they just hate? Any psychology instructors in here? Students hate that chapter. They hate Meredith. They hate that chapter, don't they? So this is a case where maybe reading twice would really help the student pick up a better understanding of these molecular aspects of psychobiology. Well, no. There's no help at all. There's nothing from reading twice that's producing any gains. And on short answer, it's the same story. It's the same story. Well, you might object. You might say, well, okay, but students don't really read the chapter once and read it again right away. What they do is they read it when it's assigned, we hope, and then they read it just before the exam. So we did that experiment. We had students read the chapter, then they came back 5 days later and read the chapter twice, or another group just read the chapter before the test. And what do we get here? Oh, sorry, this is the delayed test on the biopsych chapter. Nothing going on. So here's a week interval between rereading and then an exam. No, reading twice doesn't help at all. And reading twice doesn't help at all on short answer. No significant difference. So, the lesson here is that, number one, it would be useful for us to discourage students from simply rereading notes in the textbook. That's their number one go-to study strategy, and in fact, it's not giving them the benefit that they think they ought to be getting. What's happening? Well, let me give you a short answer. What's happening is that during rereading, the brain's receiving cues regarding the fluency of the rereading and the familiarity of the content. And these cues hijack the process of trying to develop a deeper understanding. These cues are telling students, I know this stuff. I really know this stuff. The cues of fluency, that is the reading faster, because they've already encountered this before, and they sense a familiarity with the content. And as a consequence, their metacognition, their belief about what they know, is misled. So I'm rereading, they're just saying, I got it, I got it, I got it. And they're not really digging in and understanding more. So it's seductive. The rereading seduces the student into thinking they know, and they don't really know it. All right, so what should we do instead? Well, we should try to get students to generate understanding. Instead of being seduced by fluency and frequency, somehow get them to engage in study activities that generate understanding. Well, that's easier said than done. All the faculty would say, yes, that's what we want students to do. So what are some techniques by which we might do that? One technique that's been examined quite often in the laboratory is to get students to answer the question why, or to pose the question why, and get students to try to explain about information. The idea here is this, that for students, much of the information that they're learning in the classroom seems kind of arbitrary. To the faculty member, it makes lots of sense. The faculty member has lots of connections to this information. The student just thinks that it's kind of arbitrary. A middle school science student has to learn arteries are thick elastic vessels that carry blood away from the heart. Veins are thin vessels that carry blood to the heart. To the middle school science student, this is just arbitrary information. What you can do is you could maybe try to generate understanding by asking the student why. Why are arteries thick elastic vessels? And what you hope to do is guide them toward the understanding that they're thick elastic vessels. Why? Because you've got to have a thick vessel to withstand the pumping motion of the heart, and the elasticity allows these vessels to contract after the blood goes through to act as a back valve so the blood doesn't come back toward the heart. Veins can be thin. They don't need to be strong. They're away from the pumping action of the heart. Once you get explanation, now the student's generating relations among the information. And they're relating it to a knowledge base, and they're understanding the significance of those properties. So we think that stimulating students to answer why, or other deep level questions like how. How is the digestive system like the respiratory system? That's what one biology instructor at the University of Washington in Seattle asked her students. Or you could ask, what if? Well, we know from laboratory work with simple sentences this works. What about more complex materials that we see in the classroom? So for example, what about a paragraph from an astrophysics textbook that talks about the conservation of angular momentum? This is pretty technical stuff. A body in motion has constant energy, and energy must be conserved. It takes less energy to spin as an object size gets smaller. Collapsing stars spin faster and faster as they fold in on themselves. The phenomenon of spinning faster as the star size shrinks is because of a principle called conservation of angular momentum. This is what students are reading. This is what they're learning from. So we pose the question, what if we stimulated the student to try to answer why? Try to answer why. Would learning increase? Now, this is not a classroom study. This is done in the laboratory. I'll move on to a classroom study in a moment. So we did the study where students either study these texts or the other half of the students have to answer why. Why does an object speed up as its radius gets smaller? So try to get the student to grapple with this principle. Try to relate it to things they know. And when we do that, look at what happens to learning. We have both factual questions. The text only produced about 74% correct. Answering why produces a nice increase in performance, so students are almost perfect. On inference questions where students have to solve problems, they go from 60% to 73% when they've had to struggle with answering why. So rather than reread, what we ought to be doing is trying to stimulate students, and students can do this on their own as they're studying, is to pose the question to themselves. Why does an axon transmit an electrical system down the membrane, or how does that happen? Not just reread it, but try to explain why. So would this be potent in the classroom? It's starting to be the case that some educators now are in the classroom having students do little mini writings, 2 or 3 minute writings, where the students respond to why questions. Does it work? Well, we just finished an experiment in an authentic classroom, in an introductory psychology classroom, in which we examined the benefit of these right-to-learn, we call them right-to-learn assignments. And in the classroom, there were 924 students in 6 sections of introductory psychology at Colorado State. And some of the time, sprinkled across classes during the semester, either at the beginning or middle or end of the class, these students were asked to do a mini writing assignment. This was the experimental condition. And these questions prompted an explanation, and students generated written responses. So here's an example. In psychology, you have to learn about the forgetting curve, and students were asked in a mini writing assignment in the classroom, after encoding information well, it's sometimes forgotten, draw the forgetting curve, explain your drawing to someone who's never heard of it. Why does it have this particular shape? So now we're asking students to explain why in a little 2-minute writing session. Doesn't take much class time. Everybody can do this. The control was a kind of a strong control. Rather than having nothing happening, sometimes students, instead of doing the answering why, they were in a copying condition where they were shown information corresponding to the question, and they just had to copy it word for word. So here, in this case, students would get the forgetting curve. The forgetting curve. Ebbinghaus found that most of the nonsense symbols he learned were forgotten rapidly. Small percentage of words he didn't forget were retained for quite a long time. This actually gives the answer to the why question, but all students are doing is copying it down. So, sometimes students have to do the mini writing, the explanation. Sometimes they copy. This is all balanced across the different sections. And then on the final exam, there are 24 questions. 12 of those relate to the copying, 12 relate to the why questions, and what happens in terms of performance. If you just copied, you get 68% correct. If you did mini writing, you get 72% correct. That's a statistically significant difference, and it results in a half of a letter grade improvement for the student. That's not a huge effect, but I think it could be bigger, in as much as in the classroom, people aren't going to implement a control of mini copying. Instead, they're just going to do the mini writing or not, and I think in that case, mini writing is going to produce better advances over what you get otherwise. And the other thing is, in these mini writing conditions, we didn't always ask a why question, and I think if we would always ask a why question, we'd get even better improvement. So are there ways that in the classroom with minimal changes, we can bring effective techniques to help students understand? Okay. A third point, this is really an important point, is that the laboratory work has shown for 50 or 60 years that if we mass presentation of information, retention and transfer is worse than if we space study and instruction. Now, this really goes counter to what we do in our educational system. In our classes, for example, in psychology, we might first talk about classical conditioning. We mass the discussion of that. Then we move on to instrumental conditioning. Then we move on to short-term memory. In other kinds of courses, in geology, instructors tell me, they talk about metamorphic rocks. They talk about sedimentary rocks. And so they mass instruction, and then they move on to another topic. What the literature clearly shows is that we ought to be spacing that instruction out over time. And that leads to better retention. I could show you lots and lots of laboratory studies showing this, but you might not feel that's very impactful. Instead, I'm going to show you 2 of about the 6 or 8 studies that have been published on spacing in a classroom situation. And this will give you a concrete idea of what I mean. The first example comes from a medical school. In the medical school, this is very typical. The surgical residents get trained on a particular kind of surgery in one day. So in this particular school, surgeons were trained on a microsurgery for arteries, a microvascular surgery, and as was common, this was a one-day instructional period where they looked at videos, the surgeons looked at videos, they did some practice on a synthetic artery model, and then they had a little feedback from an instruction, a little lecture. This went on for 2-hour segments throughout the day. In this experiment, the researchers randomly assigned 19 of the 38 surgeons to participate in the usual kind of instruction. And then really, really neatly, the other 19 were given the 4 training sessions, but they were given each 2-hour session once a week. So they went in and they got 2 hours of instruction, and then a week later they got 2 more hours, and a week later 2 more hours, and so on. It's the same amount of instruction. The only difference, and it's the same instruction, the only difference is the spaced group gets 2-hour segments with week intervals. Then, a month later, the surgeons are given their exam. Now, part of the exam was to redo the exercises on the synthetic artery. This is a plastic artery. And the results were that the 19 surgeons in the space group did better than the masked group. I don't have the numbers here for you. I'm not going to bore you with numbers because I want to show you something even more profound. In addition, for the first time, these surgeons had to operate on a live animal model. They were given a rat with a damaged artery, and they had to repair that artery. And what we want to look at is the percent who failed to do this. So let's look at this. Look at this transfer. This is the group trained with masked business as usual. 16% failed to fix the artery, and the animal had to be sacrificed. 16%. I have a little red bar here for the group that was taught in a spaced manner, not because any failed, but just to show you that we do have data from that group. Nobody in the spaced group failed to repair the artery. Listen, folks, I don't want to go to these surgeons who are trained in the typical way, who are given masked instruction and thus can't retain how to fix the artery a month later. I don't want to go to those surgeons. I want to go to these surgeons. But the problem is, that's not the way training is going in the medical school. It is at this medical school now. They've changed the training, so now training is spaced over time. Well, let's look at something that's less life and death, less of a life and death matter than surgery. The other thing is you could say, well, surgery is kind of a skill. It is a skill. And we know that spacing is really good for skills. Learning to play instruments, learning sports, and so on. What about the kind of information we're learning in the classroom? Verbal information. Well, this is a study that was just published last year in a middle school science classroom in which all the students have access to a little computer tutor that helps drill them on vocabulary and phrases they're learning during that week. And the researchers came in and they said to the teachers, we just want to make one small change to your computer tutors. All we want to do is program the computer tutor so that the following weeks, the computer tutor brings back for study material that was learned 2 or 3 or 4 weeks ago. So do you see what I'm saying? Instead of practicing on the vocabulary assignments for just that week, the computer tutor now practices students on vocabulary and phrases from 2 weeks before, 3 weeks before, 4 weeks before. The instruction is spaced. There's no more time spent on these computer tutors in the spaced versus the masked. No more time spent. The only difference is the studying is spaced over time versus masked. Does it make a difference for how much the students retained in terms of their vocabulary and their ability to generate short Spanish phrases? You bet it did. It made a difference. So here are the data. This is the group that got the usual computer tutor twice a week in class, massing study of that week's content. And this is the group in which the same content was practiced but spaced out over the semester. The end of the semester exam shows a nice improvement for the space group, and a 1-month delay, the improvement is even a little bit augmented. So that after a 1 month, there's even more of an advantage over spacing than massing. So again, I want to emphasize, this is a change that's easy to make in the classroom. It's easy to make. The students didn't do anything different than they did in the spaced and the masked. They still spent 2 hours a week on the computer tutor. It's just that now the content is spaced. This is something we can do in our classrooms to good benefit. All right. Fourth point. Fourth point is that we ought to intermix presentation and practice of closely related concepts. This is not what we do in education now. What we do in education now is we block the practice of similar concepts and then move on and block the practice of another concept. So for example, in math, in statistics, What we do in statistics, and they do it in business statistics, they do it in every kind of statistics, is students get practice on computing correlations, and then that's done. And then they get practice on computing t-tests in the next week's homework. That's not intermixed with computing correlations. And then they get practice at computing analysis of variance. In art history, here's what happened to me at Oberlin. In art history, it was modern art. We learned a little bit about Matisses, and we looked at lots of Matisses. Then we were done. And then we looked at some Monets, and then we were done. And then we looked at some Renoirs, and then we were done. Those paintings were never intermixed. The idea was it's better for the student if you block instruction on one type of thing, presumably so they can see the similarities and get practice on that. But the laboratory work shows that it's better to mix these things. So let me show you two examples with authentic materials. These kinds of experiments, to my knowledge, have not been done in the classroom, and I'll give you a sense of why. So first of all, this was a study of this was done in a laboratory, but it trained students to compute the volumes of 4 different kinds of solids. And these got cut off in transferring it. I don't know why. But at any rate, some students were taught in the usual blocked fashion. That is, they got instruction on one kind of solid and then practiced in computing the volume. Then they got instruction on another kind of solid and practiced computing the volume. It turns out that in all middle school math books except one, this is the way instruction proceeds in math. You get an example of one type of problem, you practice it, and then you move on to another type of problem. The mixed group got, in contrast, instruction on all the solids, and then they practiced in an interleave fashion. They got practiced on all 4 problem types. And all 4 problem types were presented in random order. And then a week later, they get 8 novel problems, 2 from each kind of solid. And let's look at what happens, first of all, in practice. In practice, the blockers, over the course of their practicing, are getting about 85% of these correct. So the performance is very good. The mixers, on the other hand, are struggling. They're only getting 60% correct. So on a performance standpoint, what's happening is the student who's got blocked practice is saying, I've got it. I'm really doing well. I feel great. And the instructor is saying, my students are doing marvelous. I'm a great instructor. Look how good my students are doing in the block situation. The mixers are struggling. What happens a week later when we bring the student back and we say, do these problems for me? Look at what happens. Look at what happens. Look at what happens. The blockers can only solve 20% of the problems a week later. The mixers have not lost anything. They're still at 60%. It's harder to solve these problems when they're randomly intermixed. Students don't like it. They don't perform as well. But everything they learn, they retain. If you block stuff, students have a feeling that I've got it, and a week later, they can't do the problem. Did you recognize this, faculty members? Do you recognize this? All right. Well, I think this is a problem in our education, and it doesn't take any more instruction to block versus mix. It takes a little bit of change in the way you're going to assign homework and so on. So what's happening here? What's happening here? What's happening is this. The blockers a week later didn't forget the formula. They didn't forget the formula. What couldn't they do? What couldn't they do? They couldn't figure out what formula went with what problem. That's where they made their mistakes. Why? Because they never had to practice that. When you block instruction, you know what formula you're going to use because that's what you keep practicing. So what we do to students is we deny them the opportunity to learn the very skill they need, which is when they get out of your classroom and they get a data set. Should I do a correlation? Should I do a t-test? Should I do an analysis of variance? How would they know that? Because all they've done is practice correlation, then move to t-test. What you need to learn is not only the procedures, but where to apply them. When they get out in their jobs, How do they know what to use where? They don't if you've blocked instructions. All they do is practice one type of problem that they know how to solve. So this is another, I think, fairly modest change that we can make in the educational system that's going to produce big benefits. Now, students won't like it because it's harder, and instructors don't like it because they tell me students aren't going to like it, I'm going to get bad teacher ratings. So this is going to be, it's going to be kind of practically a hard change, but I think if you inform students as to why you're mixing up their homework problems so that it's tougher, students will buy in, and you'll get better learning. All right, last thing, because I'm told that people will want to ask questions. So 4 more minutes. Oh, well, I want to show you a similar thing. It's not just learning math problems, but it's art concepts too. So an experiment was done in which artists who weren't well known, so the students wouldn't know the artist, and maybe if you look at the artwork, you can see why. I don't know. But at any rate, students were either taught, they were either studied 6 particular examples of one artist, and then 6 of another, and 6 of another, or they were intermixed. So they would get 1 from one artist, 1 from another artist, 1 from another artist, and so on. And so we're going to ask the same thing. Is blocking better or is mixing better? And now the test is going to be, students are going to be given new examples from these artists, and they have to identify who painted this painting. This is exactly what I had to do in art history class. Here are the results. So these are the mixers. This is the percent correct on new paintings they had never seen in terms of identifying the artist. And look, they outperform, they almost double the performance of the blockers. And the experimenters didn't believe this because there's this strong intuition that students need to see the similarities among the examples to learn it. The experimenters didn't believe it, so they did it again. And again, it's exactly the same result. Okay, if you're intermixing these examples, you're doing more, you're learning the concept better than if you block them by category. So the lesson here is that similarity may not be the thing that we have to forge. What we have to do is forge information about the differences of items across categories, and intermingling accentuates those differences. Now, let me make another comment about why this is going to be hard to introduce in the classroom. At the end of the experiment, after this transfer task, the students were all asked, what did you learn? How did you learn better? The students all experienced either blocking or mixing, and 85 of the students said, I learned better when I saw the things blocked than when they were intermixed. 85% of the students. So we have a disconnect between your metacognition. The student thinks they're learning more when you block stuff, but in fact, completely the opposite is true. So this is one of the points that Rick mentioned earlier. What people's intuitions are about learning sometimes is dramatically wrong. It's opposite for the better ways to learn. So this is going to be hard because students are going to feel they're learning more here even though they're learning more here. Okay, finally. So the final thing is this. In education, it is common to believe that when we test students, we're basically getting a dipstick into the student's brain of what they know. The test is a dipstick. We pull it out. If they get 100, great, they knew a lot. If they get 50, they didn't know so much. And it turns out that laboratory work has shown that giving a test is not a neutral event. That is, giving a test changes memory. The act of retrieving information from memory modifies it, it reinforces it, makes it more robust, so that retrieval itself is producing learning. That is, what I'm saying is that we shouldn't think of tests just as assessments. We should think of tests as ways to stimulate learning. We should think about them as learning activities. So the implication is that we ought to be giving a lot more quizzes in classes, a lot more quizzes. And in college, you don't see many quizzes. Because quizzes allow students to practice retrieving information, which is what they have to do on tests. And it also probably promotes consolidation. So there's some classroom studies that show this very nicely. We did this an introductory psych class at University of New Mexico because 30% of the students were failing, and the dean said, I'm not going to accept that, fix that course. So what we did was we set up a situation where students could be accessed online quizzes on content. So for example, a quiz item might be on sensory interaction. You can read it. And then an exam question would be on sensory interaction, but it would be a different question. So the student has to be able to transfer from the quiz item to the exam question. And then on the test, items that had been previously quizzed online those questions are answered much better, much more accurately than items that aren't quizzed. In fact, you can see items that aren't quizzed, students are responding at a failure rate. So, and we can show also that sections that are required to take the quizzes versus sections that don't do much better. This is low stakes quizzes. Students aren't getting graded for how they do on the quiz. They're getting a couple points for simply getting online and taking the quizzes. So I'm not talking about increasing high stakes testing. That's not what I'm talking about. I'm talking about low or no stakes testing to improve learning. Here's another situation in an in-class quiz, and you can do quizzing in class. I do it in my class because I tell my students about these data, and 5 years ago they said, and you're not quizzing in class. There's something wrong here. We know quizzing is useful. Why aren't you practicing what you preach? I said, you're absolutely right. So now I quiz in class. These aren't my data, but a section that has no quizzes, these are really 2 or 3 minute quizzes at the end of class, is doing worse on remembering the statistics in a section that has more. And now let me give you finally an example from biology. In biology, one of the things that seems to be percolating through higher education is the idea that we ought to be examining students to perform on high-level questions, questions that require application, synthesis, and integration, rather than just questions to see if they've memorized facts. And one of the things I want to that we thought is that, well, maybe these application and synthesis questions not only test students' ability to do that, but it promotes more learning. So we did an experiment in an introductory biology class at Brigham Young University. And the experiment was conducted across 2 sections of biology. They were identical in terms of the instructor and the content and the way the course was taught, but they had one major difference. And the difference was that in one section, all the quizzes and unit exams were given at questions at low levels of Bloom's taxonomy, at remember levels. In the other section, all quizzes and exams were given, had questions that had apply, analyze, or evaluate. So we have a low-level testing condition and a high-level condition, and what we wondered was, how do students perform on the final exam now on different questions? And all sections are now given the same final exam, and the questions incorporated into the exam are both high-level and low-level. So what happens? Well, for you biologists in the crowd, this would be a low-level question. In humans, the haploid number n equals, shout it out if you know it. Okay, well, here's the answer. And then the high-level questions would be, you get a little scenario, and you've got to infer and apply information to this scenario to answer the questions. That's an example. Just for you biologists in the crowd, I didn't want to leave you out. Here are the results. For high-level final exam questions, perhaps not surprisingly, the section that had high-level questions throughout outperformed the section that had not. It's maybe not so surprising. The neat thing is that on the low-level final exam questions, the group that only had high-level questions throughout is outperforming the group that had low-level questions. So here's a case where forcing the student to grapple with application, synthesis, and integration actually helps them learn more of the underlying concepts and facts that are tested directly in the low-level condition. All right, so that's it. I want to sum up. Take-home points. Rereading is not necessarily effective. It can be, but the way most students engage in rereading is not effective. It's just recycling and repetition. That's not effective. We ought to discourage it. Students should not be doing that. You're not using your time well. And I can guarantee you, if you're spending lots of time rereading, you're probably not getting the kinds of grades you want. Secondly, to foster retention and transfer, we ought to, instead of rereading, we ought to promote elaborative study activities. We ought to get students to think about trying to explain the constructs and concepts that we're teaching. Thirdly, introduce spacing and interleaving into courses. This is not a big adjustment. So Rick Moog in chemistry does this through quizzing. He quizzes one day, today say, if he has chemistry, the quiz is on material that they covered last week. So in that way, he's spacing material over the class. So quizzes can be used that way. Homework can be used to space material. We have a psychology instructor that builds in time in her classroom every day to revisit material from previous weeks. It's an adjustment, but it's not a major overhaul. It would give big benefits. And finally, testing promotes learning and transfer. We ought to be relying on low-stakes or no-stakes tests to help students learn. It should be testing's more than just an assessment device. It's a learning tool. And I would suggest to all students that they ought to self-test in preparation for an exam. One, and I don't have time to show you the data, but I can tell you about it later. One really effective technique is to read and then try to recite that information, either to yourself. I have a student in my class who says she recites it to the wall. She tells the wall about what she learned in class and what she read. Or tell a friend, or think about it on your way to the cafeteria, or when you're in cross-country practice. Try to start reciting what you've learned. And then after recitation, review. Read, recite, review. Testing doesn't just strengthen memory, it informs you about what you know and what you don't know, so it more effectively guides your study activities. And I have data on that, but I've run out of time. So thanks very much. Thank you. So we have 8 to 10 minutes for questions.
Hi, my name is Emily Meneghina. I'm a theater and Italian major, senior. But one of the initial points that you made, I wanted to ask you about different countries where the schooling is based on rote memorization. I've taught in Italy and I've visited high schools in China where that's kind of basically how it goes. And activities about working together and such aren't really a part of that curriculum. Are they doing, is there research over there that's also supporting the research doing here without being like this Western research needs to be adopted by the entire globe, but so why are those methods still being held up? Because are they finding over there benefits of that?
So the question is, in other cultures, the educational system may encourage more rote learning than maybe we do in our universities here. And that may be the case. I don't want to make a value judgment about that. What I will say is that all the methods that I've been talking about are perfectly useful in those situations as well. In fact, they're very useful. So if you've got to learn a lot of math facts or a lot of vocabulary or whatever, rather than just reading these over and over, which is what most students do, practice retrieving them. Space your practice. All of those methods are equally useful for remembering individual facts in a rote way or for trying to build better understanding. So yes, these techniques, I think, are universal. Yeah.
Hi, my name is Fato. I'm a junior. And this year, I am also a preceptor, or I don't know, maybe you might, in your universities, TA in a class. And my question is about, has FNM right now is about to get into finals, and I guess going back to your point about spacing, learning, and time, and we are right now, everybody's under stress. So
Yes.
if you could talk a little bit about stress and memory and learning, especially in these next couple of weeks that's going to be for students, that would be great.
All right. Well, I don't have a lot to say about that from a data standpoint. Okay, I haven't done a lot of work with that, but I can tell you this. we have gone into middle schools in our surrounding St. Louis area and implemented quizzing programs, no-stakes quizzing programs with clickers. And in interviewing the students, we just did this in the last year afterwards, we asked them, how anxious were you about taking the test in your classroom? And did the anxiety seem to be less after a lot of quizzing? And the answer was, most of the students said, the quizzing really helped me with my anxiety levels. So after I got a lot of practice in quizzing, I wasn't nearly as anxious for the exams. So to the degree that anxiety is stress creates anxiety, the answer is this: sure, you want to lower stress and anxiety, and one way to do it is to practice the kinds of cognitive activities that are going to be demanded of you on the test. And those are retrieving information. So practice that during the week. Practice giving yourself tests. Practice taking quizzes. Practice with flashcards. That reduces anxiety. It reduces stress. The other thing is that I would really advocate spacing the study. So if students are waiting to the last minute to study, that's really stressful. That's really stressful. You can reduce that by creating a study schedule where you're studying a little bit on one day, a little bit on the next day, a little bit on the next day, the material, and keeping to that schedule. And in my opinion, that reduces stress. I don't have evidence on this, but my intuition is that reduces stress dramatically over the student who's trying to cram everything in the night before the exam. So stress reduction means planning. Stress reduction means management of study activities, making sure you're spacing those study activities. So I think the answer is yes. These techniques also should be useful for reducing the stress associated with learning, because these activities are producing permanent learning. They're producing robust learning. And with that kind of thing in hand, students can go into their exams and feel comfortable and confident and do well. I mean, oh, sorry. So let me just tell you briefly, really briefly, about the story about a medical student who adopted these techniques. Even before our book was out, he would just read our websites, what we were doing. And he said he was flunking out of medical school and a lot of anxiety. He really wanted to be a doctor. And he implemented these methods of self-testing and spacing his study and trying to explain things he was learning. He's now at the top of the class. He's not stressed at all. This guy's having a good time in medical school. So I think these techniques, they do involve work, but learning is work. But if you know where to put your energies, I think your stress kind of disappears.
Hi, my name is Rebecca Marshall. I'm a history professor, even though I look 12. So I really liked your talk.
You look 15, not 12.
Yeah, 15. I really enjoyed your talk. And one question I have, so I was struck that you were telling us how we could increase student mastery and student learning. And as a new faculty member, and I'm only visiting too, so this is, one of the concerns that I have are how to demonstrate that I might have student mastery, but my class is also intellectually rigorous. So there are sometimes a disincentive to show that you have a lot of high marks in your classroom, which you could read as evidence of student mastery, or you could read as grade inflation. So
Yes,
I was just
right.
wondering if you had advice for sort of how to approach that issue if you're a newbie, or questions of how to change institutional culture here or anywhere about culture of hardness. I'm going to sit over there.
Well, changing institutional culture is really hard. It's really hard, and we're trying to work on that at WashU, and I could talk to you more about that, but it involves talking to departments about what their goals are, and then thinking about introducing some perhaps other goals, and talking about doing things they might do to reach toward those goals. So departments who are already, it's departments who are already looking for goals to say, let's increase the intellectual richness of the student's experience. Those departments are easier to work with, but basically you have to work with the whole department. You have to get buy-in from the department. You have to help them identify the goals. You have to help them identify the steps that we're going to take as a department to move toward those goals. So it really takes a department-wide effort and maybe some assistance. There's something called, the COCO model of change. I don't know if you've seen that book. And a woman from Boise State has used that quite successfully to implement cultural change at Boise State for having departments reach for the kinds of goals they want to reach for and changing curricula to do that. But I don't know what to say about grade inflation versus all students achieving a certain amount of learning. I mean, personally, I give exams that I think are really challenging, require integration and so on. And if the students are doing well on that, but I'm also using lots of quizzing, and I'm using things that I think should promote good performance. So if many students are performing well, I take that as a sign that good, they're really learning the material, and I don't worry too much about the fact that many of them are getting good grades, because I would put these students up against any other student and say, test my students, they really know what they're talking about. Yeah, Tim.
What does your research about how individuals learn best and how to assess individuals, what does that add to the debate about high stakes testing as a tool for other means in elementary and secondary education in terms of using instruments, standardized tests to determine funding and teacher qualifications and things like that?
That's a really good question. I'm probably not going to answer the question. I'm not going to answer the question. I'm not going to. I think testing's fine if it is designed to align with your learning objectives. So I think the problem with testing is that often, and I'm not going to necessarily speak about standardized tests, but often instructors unwittingly give tests that aren't aligned with the kinds of learning activities that they're having students do. And I think this is where the big damage is done. So, for example, in AP World History, there is now, I think there's a manual for the instructors that suggests that instructors have students construct matrix notes. Have you ever heard of this, matrix notes, where you list each civilization at the top of the matrix, and down the rows you list different characteristics, the religious orientation of the civilization, the economic orientation, the political orientation. And students are required to synthesize and summarize these aspects and to draw relations. I actually have a slide, but I have it hidden, so I'm not going to go over and show it, that shows the students' matrix notes. And you can see they're doing lots of arrows here and lots of writing. And then the instructors, I've heard this from the West Coast to the Midwest to the South, from students in my class, they say the instructors give an exam, a multiple choice exam, that focuses on nitty-gritty details in the civilizations. So now what you have is you have this big mismatch between an effective, these matrix notes I think are very effective for getting integration, synthesis, organization, but the exam is not tapping into that. And as a result, the students are floundering in these courses, and also what it does is it devastates their metacognition. I have data, but I've run out, I can't show it to you, that if you give these mismatching exams with their study activities, students can't predict how they're going to do in the exam. They have no idea of what they know and don't know. And so their study policies, students are rational, they're going to study things they don't know. But if their metacognition is completely inaccurate, they're at chance in what they're studying in terms of whether they're studying things they know or don't know. And that's the problem, is that if our testing is misaligned with our learning objectives, then you're going to get poor performance, and not only that, students' metacognition is going to be completely undermined. They don't know what they know and don't know. They don't know how to predict how they're going to do. I think, so to the extent that's happening, I think it's bad to the extent that's happening. I can't tell you how much it's happening. I haven't looked at these things, but I know it's happening in some individual courses, unwittingly. I don't think faculty are mean, or they're not trying to hurt the student, but it's just an unwitting kind of thing. So I think tests ought to match up with the learning objectives. And if they do, then I think that's absolutely positive. So I know I didn't answer your question, but those are my views on it.